Hey, welcome to video number 43. In the last video, we found LiDAR data of the Middlebury River Gorge and converted it from point cloud format, or .las, into a raster digital elevation model that we can now use to do some analyses. So our ultimate goal with this data is to map out terraces along the Middlebury River and also to extract river profiles through the Middlebury Gorge and compare the slope of the modern river to the slope of the ancient river as expressed on the terraces. So in this video, I want to show you how to use basic hydrology tools to make a couple steps towards extracting a river profile from the digital elevation model. And then in the next video, I'll show you how to actually extract the profile. So there's a set of hydrology tools in ArcMap that are commonly used to route the flow of water across the surface of the landscape. And this has a number of applications. The most important application is this helps us identify where river channels are. But of course, it also helps us think about routing floodwaters and a whole bunch of other things. So in this video, I'll introduce you to the three basic steps or hydrology tools that are used to compute the routing of flow of river water. That's the fill tool, the flow direction, and the flow accumulation tool. Then we'll apply each of these hydrology tools in ArcMap to start delineating our own river channels. So the fill tool is pretty simple. It's designed to fill closed depressions in your digital elevation model. So if you have some depressions, the fill tool will actually resurface those and level them off with a flat plane connecting the spillover point of the closed depression. Now importantly, the main purpose of this tool is actually to fill artifacts in the DEM, or mistakes, where there's accidental closed depressions that would ruin your flow routing. But it's important to know that when you use the fill tool, you're also going to be filling real depressions that might actually have some geologic significance. So the fill tool is a good way to route water flow, but it's bad if you want to study microtopography. This is especially important for LiDAR data, where the really high resolution of the digital topography actually reveals a lot of closed depressions. Okay, the second step, once we've filled our DEM, is to compute a flow direction. And we do this with the flow direction tool. And the algorithm for this basically considers each pixel in turn, and it asks, from this pixel, into which neighboring pixel would water naturally flow? And of course the answer is the water will flow downhill. Or in other words, it will flow into the pixel, the adjacent pixel, to which it has the highest gradient. So this algorithm computes the gradient or slope between each pair of pixels. And you can see those calculations here. The highest pixel, the highest gradient, is going to be 0.5 between these two pixels. So that center pixel then is going to get assigned a flow direction to the southeast, which will be coded by some raster value in the flow direction raster. So the third step is to compute flow accumulation into each pixel. And the way this works is that the algorithm starts at any given pixel, and it asks which neighboring pixels are flowing into this pixel. And then for each of those in turn, it will follow that pixel uphill, counting the total number of pixels that are pouring into the given pixel. So for this particular pixel, we've got water coming in from this direction, water coming in from this direction, and from this direction. So we'd have to count many of these upstream pixels. And we'd assign a number to this pixel, and that number would represent the actual number of pixels that are contributing water to it. So pixels that are further downstream have higher values, pixels that are upstream have lower values. And then you'll see in a minute that we can color code the flow accumulation raster to draw out where the channels are. A fourth tool that we won't be using in this video is called the Watershed tool. Once you've delineated your flow accumulation raster, You can run the Watershed tool to just start at any point and work headward until it reaches the drainage divides, and then actually determine the bounding polygon that incorporates the watershed. And that's pretty handy if you're studying flows of pollutants or flood hazards or a whole bunch of other things. But we won't be using that tool. With that introduction, let's jump right into applying these tools in ArcMap. So remember, we left off in the last video and I asked you to make this hillshade. So you should have an image that looks something like this, perhaps with a different color scheme. Notice that things came out pretty well. If you zoom into some of these areas, we can already see some beautiful river terraces here. We can see roads cutting across the landscape. So there's going to be a lot of fun stuff to map on this image, and we'll come back to that in some later videos. For now, let's work on extracting the river profile right up the Middlebury River. So let's run our first tool. That's going to be the Fill tool. That'll be under Spatial Analyst, Hydrology Tools, and then Fill. So I'm inputting my LiDAR DEM. I've got an output called midgorge_fill with a .tiff extension. And I'm going to leave the Z-limit blank, which means we're going to fill all the holes, not just shallow holes. And I'll hit OK. Okay, so my filled raster has popped up. It looks very similar to my unfilled raster, but without the holes. So the next step is to compute the flow direction raster. So I'll use the flow direction tool under hydrology. Now importantly, notice that the input raster here is actually my filled raster, not the original one. If I were to use the original, all my rivers are going to wind up in closed depressions. I've got an output here, which I've given an appendix of flow direction, and using the .tiff extension as well. So I'll hit OK and compute that. So my flow direction raster has popped up now. Notice it's a classified raster. It only has about 8 values, 1, 2, 4, 8, 16, 32, 64, 128. And each of those simply denotes whether the pixel has a steepest gradient to the pixel towards its left, towards its right, above it or below it, etc. So that's what's coded here. And really this flow direction raster doesn't have a whole lot of use except for being an intermediate raster that's going to now let us compute flow accumulation. So again, that's going to be under hydrology tools, the flow accumulation tool. Now notice this time my input is going to be the flow direction raster that I just made. So it's not the fill or the original DEM, it's the flow direction raster. Gave my file name an ACC extension and then a .tiff extension still, and I'll hit OK. Okay, so my flow accumulation finally finished. That took quite a while. Now let's think about how we can visualize this accumulation raster. First, let's get rid of these intermediate rasters that we made. We don't need them anymore. The thing to remember about the flow accumulation raster is that each pixel value represents the number of upstream pixels that are contributing water into it. So higher numbers mean that you are more downstream and that you have a larger upstream watershed area. So the way I like to visualize the accumulation raster is by doing it as a classified color scheme, okay, with only 2 classes. And I have one class that's going to be river channel and one class that's going to be not river channel. So I'm going to make my cutoff at around 10,000. So if you have a value of higher than 10,000, that means you're a river channel. If you're less than 10,000, you're just a spot on the hill slope. I'll hit OK. I'll color the hill slope spots no color, and I'll color the river channels blue. Hit OK. And you can see this isn't a perfect display, but it's definitely delineated all the river channels. So if we zoom in on the Middlebury Gorge here, we can indeed see that the pixels with high accumulation that are actually in the riverbed are blue. Everything else is clear. And so this actually worked out pretty well. It's definitely delineated the river channel in the Middlebury Gorge. However, notice there's a couple big problems. Take a look at this channel coming off the hill slope. It's coming down its normal valley, oops, hits the road, and actually gets deflected down the road. So here's a case where there's a culvert going into the under the road, or a bridge perhaps, so this channel should have continued under the road and down through here. You can actually see it in the topography. But what happened, of course, is that we ran a fill operation that just filled this up behind the road, and then the river spilled out at the easiest point and actually ended up flowing down the road until it joined this river. So this section of the river is completely erroneous. And if you look around a little bit, we're going to see a bunch more examples of that. Take a look at the other side of the river. 3 brooks coming off the hill slope, each of them getting deflected at the main road and flowing down the main road. And in each case, there's culverts that actually go under the road there. So it's important to recognize that this hydrology flow accumulation calculation didn't work out perfectly here, but it was good enough to basically trace the main channel of the Middlebury River, and that's what we're really after. So this was good enough for our purposes, but it's really important not to misuse these tools and always check and make sure your result is reasonable. So to sum up, we've learned 3 steps that are involved in routing the flow of water across the landscape. That was the fill step, the flow direction, and the flow accumulation. Please join us for our next video where I'll show you how to take that accumulation raster and actually directly extract a river elevation profile from it. Thanks.